Okay, welcome and our continuous review here. So we just have a little bit more, I think, to talk about, and then we'll kind of be done. And again, final is tomorrow. Also, your exam from yesterday will be up a little bit later today as soon as I get done here. I've been teaching all day, and I've been reviewing all day. I think I've now reviewed entire first semester general chemistry, and now I'm going to finish up here the second semester all in one day. Next semester, I'll just teach one day of class and be done with it, hopefully, before doing the entire semester. All right, so hopefully my voice will hold out for the rest of this. And again, like I said, I'll post up, obviously, your scores from yesterday a little bit later when we're done here. It should be up there for you to take a look at and stuff like that. Okay, let's see. So we're off to, I think, chapter 19, and this stuff should be getting pretty, hopefully, rememberish and familiar to you, I hope. This is getting into nuclear chemistry, I think, or whatever that chapter was. And in nuclear chemistry, remember, we talked about nuclear reactions, and there's several different types of particles, but basically radioactive decay is that process where either spontaneous or sort of non-spontaneous, an atom will basically start to sort of decompose, for lack of a better word, or decay. And the difference when nuclear sort of reactions in nuclear chemistry than sort of regular chemical reactions and stuff is, unlike in chemical reactions where we do have conservation of the elements that we start with, in nuclear chemistry we do actually produce new elements. So we don't have that conservation of the elements like we do in a traditional nuclear reaction. And usually we have some different sort of particles we talked about. We have alpha particles, we have beta particles, we had positron particles, we talked about protons as well, neutrons. And remember that, you know, all these guys sort of had some symbols that were used. For example, alpha, you know, sometimes the alpha symbol with a 4 and a 2 are very common in sort of nuclear chemistry. They use a helium nucleus, which is sort of what it is. Our beta particle also sometimes used some different symbols, including the beta symbol with a 0 and a -1 going on. Or because some people consider it just an electron, the E is used for an electron. We also had our gamma, right, symbol. Other ones, protons, either a P or, you know, a H is used for a proton. We also saw our neutron that's used. Let's see, our positron, right? That would also have similar sort of symbols. Also kind of the beta symbol, except that it is a positive one rather than a negative one. Or again, also even the E is used for that one as well. In terms of symbols, remember that when we write the sort of guys, number up on top is the mass number, number on the bottom is the atomic number, and the importance of that, right, is the atomic number is your number of protons, while your mass number is your number of protons plus your number of neutrons. And in terms of the periodic table, this is our atomic number. And as we talked about, hopefully you know, this number here is the atomic mass, not the mass number. So the mass number, again, not found on the periodic table, just the atomic number. And when you figure out how many protons, neutrons, electrons, mass number, atomic number, essentially all those should be positive whole numbers, right? And obviously if you look at the periodic table or a periodic table And you see those numbers on the bottom there. They are definitely, in most cases, not whole numbers. They have a lot of decimals, and those are the atomic masses. Which usually confuse people is it's usually a number very close to like the mass number, but these all should be whole numbers. Out of all those numbers, in terms of elements, right, it is the atomic number that is the most important. Everybody on the periodic table, again, if you look at it, has a different atomic number, which means they have a different number of protons. And as we talked about, what that essentially means is the identity of an element can be found solely by looking at the atomic number and using the periodic table. So that's really important, especially when we were talking about balancing nuclear equations. And when we balance nuclear equations, because we don't have that conservation of elements, and we actually do produce new elements along the way, and that's why in order to produce new elements, we need to change the number of protons. And when we change the number of protons, that means we need to get into the nucleus, and that requires a lot of energy sort of to be moved around. And that's why nuclear reactions obviously give off a lot of energy usually, because we're really converting those protons and neutrons inside the nucleus rather than a traditional chemical reaction where we're just kind of breaking apart electrons and stuff like that, which are on the outside. So again, that's why there's usually a lot more energy associated in a nuclear process than in a chemical process, as we talked about. But in terms of balancing it, as we talked about, really not too difficult. Basically, you have an arrow. It's a nice arrow. On the left-hand side, basically, you just need to make sure all the mass numbers on the left-hand side equal all the mass numbers on the right-hand side. And same thing with our atomic number. All the atomic numbers on the left-hand side needs to equal all the atomic numbers on the right-hand side. And as we saw, again, you know, you can have something where it says, say, sodium 22 equals, we'll do it that way. Sodium 22 went through a alpha decay. So if we were to do that, we would go sodium 22 would be the mass number. We could go to the periodic table and find the atomic number, which is 11. And beta decay, any type of decay process goes through this sort of decay process. That means that that particle will end up on the product side. And what we would want to look at, as we talked about, is the atomic number on the bottom. So we have 11 on the left and 2 on the right. Should get my calculator, but I'm going to go with 9 as lucky number 9. And that would be our missing atomic number. We would go to the periodic table, and that would be fluorine. Our missing mass number would be found the same way, 22 on the left, 4 on the right. Is that 18? We'll go with that on the top there. And this would represent the balanced nuclear equation in this case. Again, everybody on top there in terms of mass numbers is the same on both sides, and also our atomic numbers are also the same on both sides as well. And this is one way that you can write this sort of equation. Another way is you're given an equation and something's missing. And again, usually if something's missing, a good approach is to start with the atomic number in the periodic table and find the missing element, and then find your mass number. A reminder as well that something missing may not necessarily be an element, and in most cases it will be, but it could be a particle or something like that. So that's why it's important with all those sort of particles that we saw over here to understand both their mass numbers and atomic numbers associated with them, so that you can do these sort of balancing of these equations and get them correct. Remember as well, decay, like I said, is usually means that particle goes off on the other side, the product side. If you have something like an electron capture, that means that's a reactant. If you have something that's been bombarded, that also means that particle will be on the reactant side of the equation. We then talked about really a little bit about stability and stability of these sort of guys. And we talked about really what is referred to as the N to Z ratio. When we look at the N to Z ratio, that is the neutrons and protons. And basically Z is the atomic number. And we can use that ratio to help us understand stability, if it's something that's stable or not. And really what we're comparing it to is if that graph, if you remember, there was sort of a, what is referred to as the belt of stability, right? Or the valley of stability. And there's really sort of, you're either too high in terms of that ratio, or you're too low in terms of that ratio, which would be underneath it. And we sometimes need to kind of move ourselves closer to that belt of stability in terms of that ratio. And if we are too high in terms of that ratio, we will see the guys go through a beta decay process. If that ratio is too low, we get a couple of options in terms of what will happen. You could have a positron emission. Or you can have an electron capture. And the reason, again, we have a couple of options here is because they both will end up giving you really the same result regardless. And remember, there's sort of levels of stability here. So if your atomic number is like 1 to 20, an acceptable ratio is like 1. If your atomic number is like 20 to 40, an acceptable ratio is 1.25. If your ratio there are your atomic number is 40 to 80, an acceptable ratio is like 1.5. So again, depending on whether it is too high or too low and where the ratio is, again, we should see movement of these guys. If it's too high, closer in and down, or again, if it's too low, kind of moving up to that spot of stability that was like on that graph. We will still use these cutoffs like we talked about as pretty much hard cutoffs. So if it's between 1 to 20, it's either 1 or it's too high or too low. If it's 1.25, it's either too high or too low. Or if it's 1.5, then again, it will be either too high or too low. That was sort of an important area of stability. There's also other sort of areas where you can look at stability and sort of maybe figure it out. And that's based on the number of protons or the number of protons and neutrons that are present. And remember, if you got sort of positive and positive on each of those, that's sort of a really good arrangement rather than say negative and negative. Not negative and positive, I'm sorry. Let me try it again. If you have even and even in terms of protons and neutrons, that might make more sense. If you have even values of protons and neutrons, that's sort of your best situation. If you have really kind of two, I'm going to say negative again, you have two odd values for both the protons and the neutrons. That's sort of the worst situation in terms of stability. You know, there's only like 3 or 4 sort of stable nucleuses under that sort of series. There's also some things like magic numbers, which are basically adding up for nucleons. When we talk about nucleons, again, and that is basically what's found in the nucleus. That's our protons and our neutrons. We also talked about the idea in terms of stability here, and just to finish up on the stability part, when you do those sort of decay processes, it doesn't necessarily mean that the next step where it does maybe a positron emission or if it does a beta decay that you're going to get something with a perfect ratio at that point. But again, as we talked about, it should kind of move you towards that belt of stability when you do that. And again, just a reminder that you know, if we did have like our sodium, whoops, 11 and 22, and we did an electron capture here, that's going to give us 10 and 22. And again, obviously, if we go to 10, that is neon. And if we did our same 22, 11, and we did a positron emission, that would also give us 22, 10, and neon. So this is what I was saying before. This is our positron emission, our electron capture. You can see the end result of both of those, again, is the same as what we would get. So again, you could do it sort of either way on that. We also talked about a decay series, and in a decay series, we have really a series of decay from a radioactive element, and it will continue sort of this decay process until it sort of decays to something that's sort of a stable nucleus in that case. And it may be several steps along that path. The starting guy is what's referred to as the parent, and the resulting guy is referred to as the daughter nuclei. And if you're dealing with sort of alpha and beta decays along the way, you can, if you're really just interested in the end result, sort of mathematically determine it. For every alpha decay that happens, you should subtract 4 from the mass number, and you should subtract 2 from the atomic number there. So you should subtract 2 from the atomic number. And for every beta decay, you can just add 1 back to the atomic number. So this is a way, if you're told, hey, this thing went through an alpha, 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 beta sort of decay, you could just add them up and go, okay, I got 1, 2, 3 alphas. So for every alpha, I should subtract 4. So I should subtract 12 from the mass number. I also have 3 alphas, which means from the atomic number, I should subtract 6. And 1 beta, which means then I should add 1 back. And again, you could kind of quickly get to the end product if those are the decay processes that are occurring. The other way you could do it is just simply do individual nuclear reactions, where the product of the first one then goes through the decay to the next one, and so forth until you get all the way down, you know, to wherever you're going to end up. So that's another sort of process where you can kind of do that and end up with sort of the right answer. Another sort of thing in terms of stability was binding energy, or nuclear binding energy. And really, nuclear binding energy is sort of the difference that occurs when we take the particles that make up the nucleon. So again, the nucleon being our protons and neutrons. So really the difference in mass between really the particles that are present, the protons, neutrons, and really electrons as well. Although electrons are significantly less massive, so a lot of times they're excluded in sort of calculations. But because the particles that make up an isotope and the actual mass of an isotope, there's a slight difference that's there. And that slight difference can be converted into energy, that mass, through, for example, Einstein's equation equals mc squared. And that mass difference between, again, the particles that make up that isotope and the atomic mass is what's known as the mass defect, which in Einstein's equation would be the m in that case. C would be the speed of light, meters per second. So you could use Einstein's equation to figure out the binding energy. Your mass defect is found by taking the mass of the protons plus the mass of the neutrons and subtract it from the mass of the isotope that's usually given to you in the problem. And when you get that, that will give you your mass defect in AMU. And obviously you would times it by meters per second. Just looking at the units here will give us AMU meters squared seconds squared. And what we need to do actually is, in this case, divide by Avogadro's number to the 26. And that will get us to kilograms meters squared second squared, and that is a joule, which is a unit of energy. So this is one way that you can kind of get to the binding energy. And usually when we do this, we usually divide it by the number of nucleons. And that gives us the binding energy per nucleon, basically here. There's also some conversion factors that we saw that you essentially can use in lieu of Einstein's equation. They're sort of really based off of it. 1 AMU of mass defect is 931.5 mega electron volts. And mega electron volts is a common sort of unit of energy, binding energy as well. And another relationship I think was 1 AMU was, what is that number? It's getting old. 1 AMU is something like, bad when I can't read it anymore. I'm getting too old to see that. But 1 AMU is, where is that at? Actually, let me do it this way. Actually, not that one. I think I'm looking for, there you go. 1 mega electron volt, that's the number I think we use, is 1.602 times 10 to the minus 13 joules. So you could kind of use these conversions here. You could read them better than I can. To sort of not have to use Einstein's equation. You could go from AMU to mega electron volts, and if you needed to, you could go to joules in that case. But the binding energy here is also used as a measure of stability as well. So the greater or the higher the binding energy is per nucleon, the greater the stability of that isotope is. So greater stability of that particular isotope will be. So for example, iron 56, I think, give or take, was the one, if you remember on that chart, has sort of the highest binding energy per nucleon and is sort of the most stable. So again, nuclear binding energy per nucleon, also another useful way to look at stability. We also talked about kinetics involving radioactive decay, and all radioactive decay follows first order kinetics. And really, it is the same first order stuff that we just finished talking about. Natural log of A equals natural log of A naught minus KT, with our half-life being natural log of 2 divided by K. Remember that when we do sort of radioactive decay here, in kinetics, we usually think about it in terms of molarity, but it doesn't have to be molarity when you go in there. It can be grams and grams, milligrams, milligrams. We also saw counts per minute of carbon or something like that. So it can be some type of unit of radioactive decay that goes into those guys. A couple important things here is obviously here, that's the decay constant here in nuclear chemistry, also known as the rate constant in regular kinetics. But the decay constant and the time, you do want to watch units because they can be in different units oftentimes. And also, as we saw many times, a lot of times you do have to sort of use both of these equations together. So a lot of times you are given the half-life perhaps, and you may not be given the decay constant. So you have to use the half-life equation to solve for the decay constant, and then you can put it in there. Remember that in terms of half-life, it's the time it takes for half of whatever you started with basically to disappear. And in terms of using anything that's radioactive, say in medicine or anything like that, we obviously would want to use something with a very small half-life. So, you know, it doesn't take a very long time. It's not really active for a super long time or anything like that. I think that was mostly that chapter there. All right, then we got into some of this fresh stuff, obviously, and perhaps chapter 21. And chapter 21 is some transition metals we talked about. And transition metals obviously deal a lot with our d orbitals, and we talked about some important trends in those ideas. A couple of things just in general about transition metals, right? They lose those s electrons first. There's a couple of exceptions in the electron configuration. Chromium, copper are two very popular ones where they actually have an extra electron in the s and one less in the d orbital. So like 3s, sorry, 4s, 4s1, 3d5 for our iron, for our chromium, for example, the end part of it. And the other one ends in 4s1, 3d10 for our copper in that sense. Obviously, they have the electron configuration before that, but that's how they end. Again, one extra electron up there, making it a little bit more stable. Also, if you go underneath them on the periodic table, you see a lot more exceptions that occurred. Some don't even have any electrons there in their s orbital. They've all been sort of promoted. They're able to do that because, as you hopefully know, right, when we talk about sort of those orbitals to begin with, they're very close in energy to start with. And as these electrons get sort of filled, you know, it doesn't take a lot for an electron to get promoted up there. And as you may also know, the reason they lose them is because, again, there's a switch in energy that occurs once we start filling the d orbitals. And again, the s orbitals become higher in energy than our d's, and that's why we basically will lose those first along the way. We also then talked about, mainly in this sort of chapter as well, coordination compounds. And coordination compounds are, again, basically made up of two things. There's a counter ion and a complex ion. Complex ion is obviously a metal in the middle, which a bunch of ligands attach. Ligands, as we've talked about, and as you know, are Lewis bases. And again, as we talked about, the counter ion could be positive, which means your complex ion will be negative, or vice versa. You could have a positive complex ion and a negative counter ion. The idea there is it's kind of like an ionic compound, so overall charge is going to equal 0 there, so everything gets balanced out. Now, when we talk about sort of complex ions, we talk about coordination number. Coordination number is the number of donor atoms attached to the metal in a complex ion. And that's really important because it does depend on the ligand, which is a Lewis base and an electron pair donor. There are certain ligands which are, as we know, monodentate. There are some that are bidentate. There are some that are polydentate, right? Monodentate means basically they bind one per, and those are things like water, NH3, Cl-. They're bidensity are guys that bind twice. So that's like our En guy that we saw, our oxalate. Also examples of that. EDTA are guys that can bind in multiple places, like he could go 6 places, for example, as well. And in terms of, coordination numbers and charge, there's sort of a relationship. Typically, guys with +1 charge in terms of the metal will usually kind of make complexes that have either a 2 or 4 for the coordination number. Guys with, a +2 charge, typically going to be 4 or 6 in terms of their coordination number, and +3 a lot of times will be 6. Gold, for example, will typically do 4 in terms of its coordination number. So there's sort of a relationship between those guys. And we also talked about the idea, for example, if we had this is a coordination compound. Again, typically our guy in brackets is our complex ion. This guy here would be our counter ion in this case. And it always goes positive to negative when you see these guys. So just by the placement of that, we see that the complex ion is a positive ion. The counter ion is negative in this case. And in terms of oxidation state of the metal, this guy is 0, nitrates -1. There's 3 of them, gives you -3. So we know here that the chromium would be +3. And that means that the complex ion part technically has a +3 charge. And that is why we need not 1 of these nitrates, but as you can see up there, we need 3 of them to balance out the +3 charge there, like normal. Now, in terms of naming these guys, we talked about naming them. We do just like normal. We do our cation first, followed by our anion. And we do alphabetical order for the complex ion part. We do the ligands in alphabetical order, regardless of the prefix. With the metal coming at the end and a Roman numeral. So the metal is always the last part of the name for the complex ion part of it. And again, we always include a Roman numeral to indicate the charge on the metal in the complex ion. Again, some ligands have special names like water's aqua or aqua. NH3 is amine. We also use prefixes if we have more than one ligand, like di, tri, tetra, etc. If we also remember have kind of a ligand that already contains a prefix in it, then we have to switch to bis, tris, and tetrakis for 2, 3, and 4. Again, if they do have that prefix in it to begin with. In addition, the other kind of weird thing is if our complex ion is negative, we go with sort of the old way of naming the metal, and those are the guys that end in 8, basically. So they end in 8. So again, iron becomes ferrate, copper becomes cuprate. I think I put an extra P in there for free. Plumate, arginate, stannate for tin, and so forth. So remember that when we name these guys, it's important to figure out, is it a positive complex ion or is it a negative complex ion? If it happens to be a positive complex ion, then obviously we just use the regular old name of it. It's only when those guys are negative that we need to use that old school name. Again, always a Roman numeral. And as we saw in sort of that activity that we did in the lab, it is possible to have sort of a neutral complex ion, as weird as that sounds. And again, we'd use sort of in the Roman numeral spot 0, and also you know, in that particular case as well, we typically use Roman numerals for things that we don't usually use Roman numerals for, and that is things like zinc, for example, silver as well. So we do typically include the Roman numeral on those guys, even though on normal nomenclature, we really don't do those things. Now, in terms of the complex ions, in terms of aqua or aqua, you actually can use, you could use either one is perfectly fine. Some books use aqua for water, and some books use aqua for water. It's actually, you can use either one is perfectly fine. I actually taught one time where one book for one class used aqua and the other book used aqua, so it was like back and forth. So typically you use that one whichever way you want. The other ligand that sometimes has a weird thing that sometimes happens with it is oxalate. And with that oxalate, although you don't really see the prefix in the name, it's very common that people for oxalate use, like, because it's sort of bidentate, they'll use that like bis, for example, if there's two rather than di. So on that one, you can kind of go either way with that particular ligand as well, as we sort of saw. Other questions on that? Okay, so in addition, we talked about the idea of what happens when these complex ions in terms of really their distribution of their d electrons. And when we have these transition metals that are typically there in our complex ion, in the absence of a ligand, all of their d orbitals basically are equal in energy. But once we start to get basically a ligand that is present, we actually get some splitting that occurs of these d orbitals. And sort of in the octahedral splitting, you know, we get the 3 on the bottom, the 2 up on top, and this is our octahedral splitting. We also saw in our tetrahedral splitting the opposite sort of approach there, 3 up on top and 2 on the bottom. And this splitting of those d orbitals here is what is referred to as the crystal field splitting. And you actually can calculate it, you know, just like a normal energy sort of thing. E is equal to h times the frequency, h being Planck's constant. If you know just the wavelength, hc over the wavelength would equal r delta E as well. So you could use those sort of equations to calculate it. And that's from c is equal to the wavelength times the frequency, where we can substitute in over here. H again being Planck's constant at 6.63 times 10 to the minus 34. And then also c being the speed of light, which is that 3 times 10 to the 8 meters per second. Now we could do this, and also we also talked about that idea in terms of the color wheel, if you will, right? So, you know, kind of do that move there. So for example, you know, if we had, this was red, this was orange, this was yellow, we'll call this green, and we'll do blue and purple. And again, and just in terms of sort of energy here, wavelength, that's 560 nanometers. We'll go 580 around here. We'll go about 650 here, about 700 over here, and 400 coming this way. 430 and 490. And remember that in terms of the colors that we typically see here, we typically see, what we actually see as the color is the complementary color of the wavelength that's being absorbed. So that's why if our solution is perhaps red, we would set our spectrophotometer probably to a wavelength over here in the green area in terms of their wavelength. And again, that's going to give us sort of where the maximum absorbance is going to happen. So again, we do see sort of the complementary color to the light that's being absorbed. So again, if ours looks blue, we may set the wavelength somewhere in the orange part of the spectrum there in terms of that will be pretty much what's being absorbed and give us that maximum absorbance. So this sort of splitting occurs, and what determines sort of the splitting is that spectra series where you had a bunch of elements like I minus, Br, Cl minus, OH, got some H2O, maybe some NH3, some En, some Cn, and a little bit of CO. And sort of on this side of the spectrum here, that is what was sometimes referred to as strong filled. And on this side is sort of referred to as weak filled. And what that means is strong filled, there's going to be a pretty good separation in terms of the top d orbitals and the bottom set of d orbitals. So a large sort of crystal field splitting, a small splitting. So if you did have something, say like, we'll do Fe, and we'll do Br6, Br6. And you got something like this. Now, when we look at this Br, that is over here on weak filled, which means when they do split, this again is going to be octahedral because there's 6 ligands attached. Coordination number would be 6. So we would get that kind of splitting that looks sort of like this. And what we would want to figure out here is this is iron with a +3 charge, which means that when we look at how many d electrons it has, it will have 5 d electrons, right? As again, it would be argon. The 4s2 would be gone. We would lose 1 in the d, leaving us 3d5. So when we would go to distribute these d electrons, 1, 2, 3, it's going to go, this is small, no problem. We'll just go this way. And what we end up getting is 5 unpaired electrons. And that 5 unpaired electrons, the more unpaired electrons you have, you get something which is referred to as a high spin complex. And if you take that same iron, for example, and you hook it up with Cn minus, so same deal, going to give you the same 5 electrons here. But the Cn minus now means, for dramatic drawing purposes, we'll go like this. It's going to go 1, 2, 3 and decide that is way too up there. I'm just going to come back this way. And what we end up with is 1 unpaired electron in this particular case. And that is what is sometimes referred to as a low spin complex, less unpaired electrons. So the ligand that's attached does have an effect on, sort of the splitting that you see. And again, there may be some situations in the middle where they will tell you do it for the strong field, do it for the weak field. And there may be situations where they may not give you information and it may not make a difference one way or the other. Maybe you don't have enough electrons to even get to the top, or, maybe there's only, you'll end up with the same number of electrons if you went to the top or if you went to the bottom in terms of unpaired electrons. So sometimes there is no real difference, and sometimes they won't give you information, but obviously if there is, they will give you that information. I think that wrapped up that chapter there, I think. And the final chapter, which should be super fresh as well for you, is kinetics. And obviously in kinetics, we talked about the speed of reactions. And one thing that we talked about is basically the rate of a reaction. And if you have a reaction such as this, you could write what is referred to as the rate expression, which is the rate is equal to -1/A, change in concentration of A over the change in time. That would equal -1/B, the change in the concentration of B over the change in time. And that would equal 1/C, change in the concentration of C over change in time, and would equal 1/D, the change in the concentration of D over the change in time. Remember that we put these negatives here because they're reactants, so it should be decreasing with time, and the concentration should go down. Also, those negatives are there because the rate value, or the average rate for that reaction, should end up being a positive number, and that happens because in a reactant, the final concentration is going to be less than the initial concentration, and that gives us a negative there for our change in A, for example. That negative and negative will turn our rate into a positive number. The 1 over the coefficients is important because that essentially takes care of the mole-to-mole relationship like we talked about, and essentially you can figure out the right relationship that occurs there. This is very helpful. We don't see the negatives on the product side because they should be increasing with time, and that means that their final concentrations should be larger than their initial concentrations. This is usually helpful because it could figure out how everybody in the reaction is changing by really just one piece of information. You know, if you know how a reactant is changing, you know how a product's changing, if you know the overall rate, you're able to really kind of determine, you know, how everybody else is changing. We then talked about sort of rate laws, and remember that when we do have a reaction, say A plus B goes to C, we could write a rate law for it, which is K, A to the X, B to the Y. And the first thing about rate laws is it is only about reactants, no products. So unlike up here, just reactants are involved here. X and Y are the orders, which again are sort of the proportion that's needed to keep that rate sort of happening. And these are always found experimentally, which means usually in these cases, as we talked about, you will be given a table of information and a bunch of different trials happening. And again, you could either analyze the table or, like most people will do, sort of mathematically try to determine. You could do rate 2 over rate 1 is equal to K A to the X and B to the Y. And the goal is, when we're choosing what entries from the table here, we want to choose 2 entries where perhaps one of the concentrations remains the same and the other one varies. That's going to allow us to really figure out the orders for each of those. Once we do it for one of the reactants, we then switch it up and we keep the other reactant constant while we vary the one we're looking for. And that will allow you to get the orders here, and you could add them together to get the overall order of a reaction. And once you have sort of the completed rate law, you then can rearrange the rate law and solve for K and actually find the value of the rate constant. The way that we do that is you could basically take any entry from this table and you'll be able to just plug in the numbers. Again, you can't mix and match. You just got to plug in the correct numbers, obviously, to all of entry 1, for example, all of entry 2 in there, and that will give you your K value. We also saw that there are sort of specific orders of reactions that occur. There's obviously first order. There is second order. And there is zero order. And these are usually the most common sort of orders of reaction, as we talked about. Essentially, since most reactions are either, you know, 1 reactant, 2 reactants, maybe 3 reactants, not too much more than that, most of them will sort of end up either being first order, second order, or zero order in terms of the way that they react. And each of these have some important sort of rate laws that go with it that involve concentration versus time. So much like what we saw with nuclear chemistry, our first order is our same equation here. And again, our half-life is our natural log of 2 over K. And most importantly, the units of K for a first order reaction is 1 over seconds, or reciprocal seconds. And as we talked about, it doesn't always have to be seconds. It can be some unit of time. But for the most part, most reactions are done, you know, kind of in seconds. So that's a common unit. And if we rearrange that equation and put it in the form of a straight line, the graph that we typically associate with first order, it's the natural log of A versus time, should give you a straight line where the slope is equal to minus K. Now for second order, we have 1 over A equals 1 over A naught. Again, A naught is the initial concentration. A is sort of the final concentration plus KT. And what we see for the half-life here, it is 1 over K times A naught. So half-life is affected by the initial concentration here. And also the way we could recognize if there's no blinking lights that the reaction is second order is 1 over molar seconds. Again, doesn't necessarily have to be seconds there. It can be some other unit of time. And if we rearrange that equation and we take 1 over A versus time, should yield us a straight line where the slope will equal K in this particular case. And the last type of reaction we talked about was zero order, and that was A is equal to A naught minus KT. Half-life here going to be the initial concentration, so also affected by the initial concentration, times 2K. The rate constant here, because when you take something to the zero order equals 1, will have the same units as the rate constant, or have the same units as the rate, which would be molarity over seconds. Also rearranging that concentration of A versus time, going to give us a straight line where the slope equals minus K. If you also remember that this graph here, not the particular result of this graph, but what is being graphed here is also a first order graph of A versus time, but it is not linear. It is a decreasing with time. So you sometimes see this graph associated also with first order, and again, not a linear fit. So these equations obviously are specific for the orders of the reaction, and you would obviously want to use the correct one based on the order. And if it doesn't give it to you in blinking lights, then obviously the units here of that rate constant is probably what you want to look at to help you decide that. If you want to determine the order of a reaction and you weren't sure, you could take all your experimental information and you essentially can make all three of those graphs and do something like that on Excel and see which one gives you the most linear, so the R squared value closest to 1, and that would also tell you the order of your reaction as well. We then sort of talked about the idea of temperature and the rate. And remember that we do have sort of that, this is our reactants, that's our products. Call that energy over here. That hill, right, that the reactants has to climb basically to get to the other side is our activation energy, right? And our activation energy is sort of that energy barrier as they go from one side to the next. And obviously, the size of it will have a particular effect on how fast a reaction will occur. If it's really large, then usually the rate will be relatively slow. If it's a smaller hill, then the rate could be relatively fast. This graph that we're looking at here is actually a exothermic reaction, right? The reactants are higher in energy than our products, as opposed to an endothermic diagram or graph, which would look something like this. And here again would be our activation energy. And again, that would be endothermic, and you can see that it's a much larger hill. Also explains maybe why it's endothermic. You got to put some heat energy in there to get to the other side. When you get to the very, very top of the hill, that is our transition state. And that's usually where you have that transition state complex or that activated complex. And that is something that has sort of partially broken bonds, partially made bonds, and something that's very, very high in energy, which means it's not very stable. Things like to be in lower energy, and that's why those things will typically drop down relatively quickly. So remember as well that not all collisions will result in products being formed. They do need to collide with each other in the right orientation. They also need to have that minimum amount of energy to allow the reaction basically to occur. So one way we could sort of help ourselves get everybody up and over to the other side is through temperature. If we increase the temperature, we're essentially adding more energy, and more energy gives a greater proportion of molecules enough enough energy to get to the other side, as opposed to the opposite of that. When we lower the temperature, we have everybody kind of slowing down. So there's less molecules that would have sufficient amount of energy to get to the other side. The results of both of that is when we increase the temperature, everybody has more energy, greater amount of guys can get to the other side. The reaction tends to proceed faster. And vice versa, if we lower the temperature, then less guys have enough energy to get to the other side, and the reaction rate would typically come down. Again, very much like that experiment where you threw it on ice, it took a lot longer than the one that was heated up in terms of how fast the reaction was basically over. There's sort of a relationship between temperature and sort of the rate constant, and that's the Uranus equation. And we saw a couple versions of it, and this is sort of the graphical version of it, if you will. And this is in the form of a straight line, y equals mx plus b, which means, again, on our y, we're going to take the natural log k. On our x, we're going to do 1 over the temperature in Kelvin. This is going to yield us a straight line where the slope of this line, as you can see here, is equal to minus E of A over R, which basically means that if you do this graph, you basically take the slope of it, times it by R, which is the gas constant, and you can figure out the activation energy in joules. Activation energy is typically a positive number, which works well here because this line will have a negative slope. That negative and this negative will turn our activation energy into a positive number, which it typically is. Usually its activation energy is a positive number and usually in kilojoules. Again, you can see by the hill here, energy going in, right, to get up it, sort of a positive number. And that's why, again, it's typically a positive number when we look at it. We also can use this equation and a graph such as this to calculate A. A is that frequency factor, and that essentially is sort of that proportion of molecules that have enough energy, again, to get to the other side. And in this case, you can see here the natural log of A would equal B. To solve for that, we would take the E of both sides, and that will give you your frequency factor. When we do that, that essentially for our natural log of K gets rid of the natural log, and usually the units here will be similar to the rate constant units. And that's sort of how you can figure out the units that are associated with it by that. Now, we don't really want to graph all the time, so there is sort of a mathematical version of it, or sometimes referred to as the 2-point version of it, which is the natural log of K2 over K1 equals E of A over R, 1 over T1 minus 1 over T2. Obviously here, temperature in Kelvin. Our R is our gas constant. That's our activation energy. And again, unit-wise, also some issues here. Kilojoules usually on top, joules usually on the bottom. So again, you want to make sure that you do some conversions there of those units and make sure you get the right answer there and you're not off by a factor of 1,000. So this is obviously just one where you can plug and chug in there. You got a couple of temperatures and a rate constant. You can solve for the other one. Got 2 rate constants and a temperature. You can solve for a temperature. You obviously could solve for the activation energy as well. So we finished up talking about mechanisms and reaction mechanisms. And reaction mechanisms are really a bunch of elementary steps that really try to sort of explain how a reaction may proceed or may take place. Again, not all reactions actually go from, reactants directly to products. There may be some steps along the way that happen. For example, A plus B maybe goes to C plus D, maybe C plus D then goes to F plus G. There's some intermediates. If you add them together, things that completely cancel out, right, gives us A plus B goes to F plus G. Now, in this case, there are certain steps along the way that may be a slow step. There may be a fast step. And for example, a slow step is what is known as the RDS, or the rate determining step. And that is the step that basically will determine the overall rate of the reaction. The slow step is really the step that has to happen in order for that product to be formed. And again, a mechanism may be 2 steps, 3 steps, 4 steps, a whole bunch of steps, but somewhere along the way there's a rate determining step. Now, to know if a mechanism is sort of good or bad, there's really 2 things that has to happen. All the steps need to add up to the overall reaction. And the rate law for the RDS needs to match the rate law for match the experimental rate law, I guess is a better way of that. So the rate law for the RDS should match the experimentally found rate law. If both of those things happen, then it's a good mechanism. If that's the type of mechanism problem that you're asked about is this a good mechanism? Those are the 2 things you want to do that. Now, because we do have elementary steps, and this is, again, the only place where you could do that, you can write a rate law for each of the elementary steps by using the coefficients as those exponents. And again, this is sort of the only place where you could do that. So for these elementary steps, you could write those rate laws for them using those coefficients. And again, there's a couple of ways you can figure out which is the rate determining step. If they actually give you the rate law and it matches one of the elementary steps, then that step is the slow step or the rate determining step in the mechanism. The other easy way is oftentimes they'll label it like slow and fast, right? So, the slow step obviously would be your rate determining step. All right, well, that is Chem 1B again. Eric, in case you missed it the first time. Any questions on that there? Okay, so I think that's everything. And again, I hope this was helpful for you. A couple of things going on. Let's see. A couple of reminders that you do have sort of like a take-home quiz that I gave you. So make sure that that gets turned in by tomorrow. I think it's due. So make sure that gets uploaded. The exam from yesterday, I'll release that a little bit later here today. In just a bit when we're done here, I'll probably release it and you'll be able to see that as well. Tomorrow for lecture, not really much going on. So to be honest with you, I'll be there in case you have some questions or something like that. You're welcome to pop in and stuff like that. Otherwise, we will take the final like we normally do right around lab time at 3. And it will be pretty much the same format. So you need that the Zoom on there, right? Just obviously something to write with, a calculator, anything that was provided for you on previous exams that you may need for this exam would obviously be provided for you as well. Anything that you were supposed to know from previous exams, obviously you are still supposed to know it. And that's what we'll do at 3. And again, like I said, you don't necessarily have to come to lecture or anything like that tomorrow. If you do have a question, you can pop in and sort of chat it to me and I'll be happy to do that. To be honest with you, I don't know. This might sound really bad, but I don't know what the final is going to be right now. I'm going to write that right now as well. So I haven't finished writing it or anything like that. So I don't know how many questions it's going to be or how many points it would be. My guess is it'll be maybe slightly longer than a normal exam, maybe, but not probably super longer than a normal exam. So I imagine there might be some concepts that will be kind of put together, maybe in a problem or something like that. But truthfully, I'm still kind of working on it right now. So I'm not really sure what it will be in terms of question length and stuff like that. But again, my gut guess would be maybe a little bit more than a normal one, but not like twice as many questions or anything like that. Other questions or anything? Okay, so let's see. You got that. I think that about wraps it. I'm good for today, so why don't we knock it off, and you can go study and take care of everything that you need to take care of. And again, I'll see you tomorrow for the final. Good luck studying. If you happen to have other finals, good luck on those finals as well. But other than that, if you have questions, feel free to email me. And like I said, make sure, I think for us, we just have that quiz that's sort of outstanding. Make sure you do that. And I think maybe some online homework as well, in case you haven't finished those last couple. I think those are also due tomorrow. So make sure that you knock those out as well. All right, everybody good? All right, have a good rest of your evening and happy studying. I mean, go be happy final writing, I think.